Hey Chem Kids, Campbell here. In this video, we're going to talk about how trendy the periodic table is. So in our last video, remember I talked about how the periodic table is organized and how certain columns have names because they have the same valence electron, so they behave very similarly. Well, also, as we go down the rows in the periodic table, we actually increase the number of energy levels. And we're going to talk about that in our next unit. But remember that as atomic number increases, right, the number of protons, that means the number of electrons. And what actually happens from an organization standpoint of the atom, we get more like shells of electrons. And so the row 1 has 1 shell, row 2 has like 2 shells, 3 has 3 shells. So that variation, that's systematic going down and across, means that they behave in a systematic way for certain trends like size. So we're going to talk about atomic radius, both in neutral atoms that have the same number of protons as electrons, as well as ions. Remember, ions are those that have either more electrons, so they're negative, or less electrons, so they're positive. We're going to talk about a trend called electronegativity, which is awesome because it's on your periodic table. And we're going to talk about reactivity, which actually differs whether you're a metal or if you're a non-metal. So let's get to it. So make sure you write this down in your notebook. Atomic radius, first of all, what atomic radius is the distance from the very center of the atom's nucleus to the outermost electrons. And what's really bizarre is that on the left, as you go through a row in the periodic table, the left side is bigger than as you go to the right side. So atoms actually get smaller as you move across the periodic table. Oh, that's weird. We're going to talk about why that is in a minute. Atoms get larger as you go down. Now that should make sense, right? Because as we go down the periodic table, we add more electrons. So each shell, right, as we go down a row, we add a shell. So each row, we get bigger and bigger as we go down. But the weird part is that we get smaller as we go to the right, which seems weird, right? We're adding more electrons. So what's that all about? Well, the reason why is that when we add electrons in a row, we're adding them to the same energy level. So we're just increasing the number of valence electrons. But we're also adding more protons. And protons have positive charges, and electrons have negative charges. And the more we add, the stronger the pull is by those positive charges, by those protons. And so what happens is the more positive charge we add to the nucleus, the more they pull them in when I'm in the same row, right? When I go down a row, now I have another shell, so I have the electrons farther away. But as I go across, they get sucked in. So that's one that you're going to have to try to remember, that as you go to the right, they get smaller, because it seems counterintuitive. So on your periodic table, and by the way, if you don't have your periodic table out, sketch the shape of the periodic table on your piece of paper, on your notes. You can pause the video while you do that, because I want you to write on your periodic table, you're going to add a line that goes down this way, and you're going to have a line that points this way. So it's pointing to the bottom corner of the periodic table, and you're going to label this increasing atomic radius. So same thing down here, increasing atomic radius. I apologize for my penmanship. It's actually kind of hard to write on the screen. Okay? Now, let's talk about ions. So, as you can imagine, cations, remember cations, cats are positive. They're the ones that are losing electrons, which seems weird, I know, but as we lose electrons, remember electrons are negative, as we lose electrons, we actually get smaller, right? We have less stuff. So a cations become smaller than their corresponding neutral atom. Whereas our anions, right? Anions are the negative ones. They gain electrons. They actually become bigger. It's kind of like you're gaining weight. Did a lot of that during COVID here. So as you gain weight, you get bigger. And so as you gain electrons, you get bigger in size. So we can see here, if you look at this little periodic table, let's take a look here at potassium. Okay, potassium will lose 1 electron, and when it does that, it becomes positively charged and it gets smaller. Whereas, let's go to my friend fluorine. Fluorine here likes to gain electrons, so when it gains an electron, it gains weight and it gets bigger. So everything on the left, the metals, will get smaller because they become cations. Everything on the right becomes negative, so they get bigger. Now let's talk about electronegativity. What electronegativity is all about is how attractive an atom is to electrons. So how much it likes to pick up the electrons, and when they bond, how much the electrons are by it. So it's really about how much they love electrons. So as you can imagine, the guys that get electrons are the ones on the right side of the table. So as we go across a row, as we go to the right, our electronegativities go up. Now, there are some variations in different sublevels, so things get a little messy actually in the middle. But as in general, as we go to the right, electronegativity increases because we're getting closer to having that full octet. As we go down here this way, and don't write this on your periodic table, as you go down, it actually decreases. So that's because you have so many electrons, you're like, okay. So electronegativity is actually the highest up here. Fluorine actually has the highest electronegativity of anything on the periodic table. So let's take a look at your periodic table. So on your periodic table, you actually have the value for electronegativity. It is the top corner here. So notice how as we go up on the periodic table, we have a higher electronegativity. So hydrogen has a higher electronegativity than lithium, than sodium, potassium, etc. But as we go to the right, as we go this way, hydrogen's different, so ignore hydrogen. But as we go this way, the electronegativity, sorry, hydrogen just has helium in it. As we go this way, the electronegativity increases. So on your periodic table, what I want you to do is I want you to put an arrow that points to the right and that points up, and I want you to label it increasing electronegativity. I'm running out of room. Same thing here, increasing electronegativity. I'm just going to abbreviate it EN. Now, like I said, it's right on your periodic table. And one thing I want you to notice is that the noble gases are excluded from the electronegativity. Because remember, electronegativity is about the desire for electrons. It has a full octet. It doesn't need electrons. So this trend, this up to the right trend, only applies to everything but the noble gases. But you can just read them off the periodic table. So you can just look at the numbers. And if I asked, how does gold compare to oxygen, you could just look at the number and say, oh, well, oxygen's higher because it's 3.5 and gold is 2.4. So that trend's really much easier for you because it's just right there. Okay, how about reactivity? So the activity or reactivity is basically how reactive a metal is. And it's opposite for whether we have a metal or a non-metal. When we have metals, the more we go across the table, the less reactive they are. So on the far left, in our alkali metals are super reactive. As we go down a column and we get more electrons, because remember, electrons are what's involved in reactions. As we go down a column, the reactivity also increases. So the crazy thing is, at the very bottom of our periodic table, this corner right here, francium, is super, super reactive. It's actually very, very difficult to find. And in fact, I'll post a video separately in the Canvas class, and you can watch a video about how reactive these alkali metals are. Remember, alkali metals are in this column. They are super reactive compared to anything else on the periodic table. So on your periodic table, notice this is the same trend as you had for atomic radius. So underneath where you wrote atomic radius, I want you to write metal reactivity. So notice the trend is just the same as it is for size. So those things kind of go in hand for metals. Metal reactivity. Now what's weird is nonmetals are completely opposite. Nonmetals, as you go to the right and up, that's where the reactive stuff is. So except for, once again, those noble gases. So when we take a look, as we go across, as we get closer to the noble gases, reactivity goes up for nonmetals. And as we go up, the reactivity increases. So as you go down, they actually are less reactive. So on your periodic table, what I want you to do is notice it's the same, your electronegativity, how you made these arrows here. And honestly, we probably should have put the arrow in here for both electronegativity and for this. So this is non-metal reactivity. And the way I drew these arrows, and I think I didn't mention that on the left side, this is for increasing non-metal reactivity. Same thing here. Increasing non-metal reactivity. And again, not the noble gases. Noble gases don't react. They don't have electronegativity. They are just hanging out cool by themselves. They're like little loners on the periodic table because they have a full valence shell of 8 electrons and they are good. So in summary, on your periodic table, you should have 2 arrows to this corner for increasing metal reactivity and increasing atomic radius. So down in this corner is the biggest atom, and it's the most reactive of the metals. And then we didn't do ionization energy, so we're just going to cross that off. So this way, except for this column, so I'm going to put not noble gases. Gases. We have increasing electronegativity and increasing non-metal reactivity. All right, I'm going to have you do a little assignment now to see if you can follow the trends. So move on to your assignment. And if you have questions, just let me know.